So the last part of this chapter deals with solving logarithmic equations. So an equation has an equal sign in it, so these equations are going to involve logarithms, and like every other equation, you need to find the value or values of the variable that make the equation true. So we're going to solve logarithmic equations and verify our solutions. We're going to see that in some cases you're going to get answers that are extraneous, meaning that when you check them, they don't work. And often that'll be tied to what the domain is. We looked at before at restrictions on logarithmic expressions because you cannot take the log of 0 or a negative number. So we'll look at solving exponential equations in which the bases are not powers of one another. We'll look at problems involving growth and decay, as well as looking at applications tied to loans, mortgages, investments, etc. Okay, so on the next page, a logarithmic expression is defined for only positive values of So logarithmic expressions are defined for only positive values of the argument. So when we solve a logarithmic equation, it's essential to verify that the solution or solutions do not result in the log of a negative number. Those that do will give us extraneous roots and are not valid solutions. So recall that you have a log expression there, and actually a log equation. Well, you can write that as an exponent. Remember that a is the answer when you write it as an exponent, because this would be b to the power x equals a, and a has to be greater than 0, because you cannot take the log of 0 or a negative number. In the same way, b the base has to be greater than 0 as well, because if you use the change of base identity, it'll be log a over log b. So b has to be greater than 0 as well. B cannot equal 1, because when you convert from logarithmic to exponential, you get a base of 1. And in that case, it wouldn't matter what x is, the answer will always be 1. So having a base of 1 doesn't work, because when you convert it to an exponential, there's only one answer you'll ever get, no matter what the value of x is. And again, x is the exponent once we convert to exponential, and there are no restrictions on what x can or cannot be, okay, because x is the answer in the logarithmic form. Your answers to logarithmic forms can be either positive or negative. So, this first example, solve the following equations, give answers as exact values. We'll verify solutions as well as state restrictions on the variable. So the first step when you're solving a logarithmic equation is you want to get both sides expressed as a single log. That's one of the tricks that we're going to use. And so in this case, on the left side, we need to combine those two terms. When you're subtracting logs with the same base, you can use the quotient law to combine them. So that's what we'll do. We'll have log of x over 15 equals log of 0.2. Now, as we've seen, in some cases, we will use the uh, process of converting from logarithmic to exponential, but that's not really going to work in this case because both sides are logs, so we can't do that. But here's what we're going to do. The two sides are equal. Part of the equations are already equal, and those being the log base 10 part. So the left side is a log base 10, the right side is a log base 10 as well. Those parts are equal. So that means that the other parts have to be equal as well. So from this statement that we have here, this equation, essentially we can drop the log base 10 from both sides. And you're just left with x over 15 equals 0.2. Now, when we say we're dropping the log base 10 from both sides, it's not an actual mathematical operation. You're not dividing both sides by log base 10. You can't do that. But what we're doing is we're saying this. The two sides are equal to each other. If the log base 10 parts are equal, then the other parts must be equal as well. That is the reason why we can say that x on 15 is equal to 0.2. Okay? And then to solve for x, you'd multiply both sides by the 15. On the left, the 15's counts. You'll have x by itself. On the right, 0.2 times 15 is 3. And there's our answer. Our restriction in this case, there's only one place where we see x, the log of x. And remember that you cannot take the log of 0 or a negative number. So our restriction would have to be that x is greater than 0. Because the only place where we see x as an argument is in that first term where it's just the log of x. So that answer that we got of 3 is greater than 0. We can also check it by looking at this simplified equation right there. And if we let x equal 3, let's see what we get. So this is our check. So I'm using log base 10 of x on 15 must equal log base 10 of 0.2. And when we let x equal 3, we're going to have log base 10 of 3 over 15 on the left side. On the right side, you have log base 10 of 0.2. And we don't necessarily have to write the base 10 there, right? If we don't put base 10, that means it's common log. It means it's base 10. But on the left side, if we divide the 3 by 15, you do get the 0.2. Same thing on both sides. So we've just proven that our answer works. It is correct. So we have to do the same thing with question B. We're going to start by getting both sides expressed as a single log. On the left side, that means using the quotient law. It'll be log base 4 of x over x minus 2. And on the right side, that'll be using the product law. Log base 4 of 3 plus log base 4 of 5. We can simplify those, combine them by using the product law. That'll be log base 4 of 3 times 5. And now we've got both sides expressed as a single log with the same base. The two sides are equal. We're told that right at the start, that the left and right side are equal. Well, if the log base 4 parts are the same, if they're equal, then the other parts have to be equal as well. So x over x minus 2 must equal 15, or 15 over 1. So now to solve for x, we'll cross multiply. Subtract the x from both sides, we'll get 14x on the left, add 30 to both sides. And so x will equal 30 on 14, or 15 over 7. So there's the answer that we've gotten. Now, what about our restrictions? So if we look at the original equation, we have two places where we have the log of something involving x. The first one being log base 4 of x. So for that part, x must be greater than 0. But for the second part, where x minus 2 is the argument, there x has to be greater than 2. If x equals 2, then that will be log base 4 of 0. Can't do it. And if x is less than 2, like negative or positive 1, let's say, it'll be log base 4 of negative 1. Can't do that either. So we have to choose the statement that satisfies both of these, which would be x must be greater than 2. All numbers greater than 2 are also greater than 0. And like we did before, we'll check it. We'll check to make sure that log base 4 of x over x minus 2 is equal to log base 4 of 15. So when we let x equal 15 over 7, it'll be the log base 4 of 15 over 7 over 1507, 15 on 7, take away 2. So to subtract 2 from 15 on 7, consider 2 to be 14 on 7. So we have a common denominator. So 15 on 7 take away 14 on 7 will be 1 on 7. And to divide by a fraction, we'll multiply by the reciprocal. So instead of 15 on 7 divided by 1 on 7, it'll be 15 on 7 times the reciprocal is 7 over 1. The 7's cancel, and we have the same thing as what's on the right side. So we just showed that our answer is correct. It works. Also, that answer is not eliminated because of the domain. The domain was that x had to be greater than 2. 15 on 7 is 2 and 1/7. It's greater than 2. So what's different about this next one is that the right side is not a log. So the way we're going to do this one is we're going to simplify the left side by using the appropriate law, which in this case would be the product law, because you're adding logs with the same base. And we can multiply out those binomials. And now, this is one of these cases where we will convert from logarithmic to exponential. So it'll be 5 to the power 1. When you start with the base and cycle through, it'll be 5 to the power 1 equals x squared minus 2x minus 3. Right? Start with the base, cycle through. So we have an equation that we need to solve involving a quadratic. And ever since you first started looking at quadratics in 20-1, in order to solve them, you had to make them equal to 0. And then you tried to factor them. If that didn't work, then you'd use the quadratic formula. So to make this equal to 0, we'll subtract the 5 from both sides. So negative 3 take away 5 is negative 8. And now the factors of this would be x take away 4, x plus 2. And so that gives us answers of positive 4 and negative 2. And that negative 2 should cause some concern, because if you look at the original equation and you let x equal negative 2, in either of these two expressions, you're going to be taking the log of a negative number. So that one can't work. Another way we can eliminate it is by finding the domain. So for the first term, the log base 5 of x plus 1, the restriction for that part would have to be that x is greater than negative 1. If x equals negative 1, you'll get 0. If x is less than negative 1, you'll be taking the log of a negative number. So, and you can get that algebraically by saying originally that x plus 1 has to be greater than 0. And then if you subtract the 1 from both sides, that's where that x must be greater than -1 really comes from. The argument has to be greater than 0, then just solve for x. So in the same way, the x minus 3 must be greater than 0. So x has to be greater than 3. So the restriction that satisfies both of them would be that x is greater than 3. So that's another reason why that -2 is extraneous. It's an extraneous root because we've done all the work to find out what x equals, but this one won't work. It wouldn't check. Okay? And you can check on your calculator. If x equals 4 is our answer, if we let x equal 4 in the two spots in the original equation, figure out what they both are and add them together, they should equal 1. So when x is 4 in this first term, 4 plus 1 is 5, that's log base 5 of 5, which is 1. But you can do it on your calculator. Log base 5 of 5 plus, when x is 4 for the second term, 4 minus 1 is 3, it'll be log base 5, 4 minus 3 is 1. It'll be log base 5 of 1. That's asking 5 to what power is 1? The answer is 0. You're going to get 1 plus 0 on the left, which equals 1 on the right. But again, you can just punch it in your calculator. Log base 5 of 1. It equals 1, which is what the right side is. I want to show you one more thing. The ones we did in the previous page, we have both sides expressed as logs. You could do that here if you wanted to by expressing 1 as a log with a base of 5. 1 could be written as log base 5 of 5. Then, on the left side, you'd have log base 5 of x squared minus 2x minus 3 equals log base 5 of 5. If you wanted to, instead of leaving it as 1, you could write it as a log with the same base as the left side. And then, because both sides are expressed as single terms with the same log and the same base, you can drop the log base 5 from both sides. And you'd be left with x squared minus 2x minus 3 on the left equals 5 on the right, which is exactly what we had here. So expressing the right side 1 as a log, then you can do it the same way we did the previous questions. Dropping the log base 5 from both sides. You get the same answer. Okay? Question B. Before we can convert from logarithmic to exponential, we have to have one side expressed as a log, a single log. And so what I would do as a starting point for this one is I would subtract the log of x plus 1 from both sides. And then we can use the appropriate law in order to combine that left side. And because we're subtracting logs with the same base, that would be the quotient law. So this log is a common log, which means it's base 10. No base indicated, which means it's base 10. And now, in this case, I would convert from logarithmic to exponential by starting with the base and cycling through. I'll get 10 to the power x equals 8x take away 4 over x plus 1. I'm sorry, 10 to the power 1, not 10 to the power x. So 10 to the power 1 is 10. Make both sides a fraction. Cross multiply. And you'll have 10x plus 10 equaling 8x minus 4. And then we're going to solve for x. We'll subtract the 8x from both sides. Subtract the 10 from both sides. And divide by 2. Yeah. Oh, I'm sorry, it is plus 4. That's going to change things. Thank you. We would have found that out when we did our check. So 2x plus 10 equals plus 4. And so when you subtract the 10 from both sides, you'll get negative 6 on the right, and then negative 3 for x. Which can't work, because if we look at what our restrictions are, for the first term, 8x plus 4 has to be greater than 0. So 8x has to be greater than negative 4, and x has to be greater than negative 4 over 8, or negative a half, which negative 3 isn't. And then for the second part, x plus 1 must be greater than 0. So x would have to be greater than negative 1. So the statement that satisfies both of those would be that x is greater than negative a half. That's the restriction. And that's another reason why negative 3 won't work. But if you let x equal negative 3 in either of those two log expressions or terms, you'd be getting the log of a negative number. So in this case here, there is no solution. And we saw this yesterday, that you can use your graphing calculator to check these. So let's do that for this one. The work we did is telling us there is no answer. No answer, no solution. No place where these two graphs equal each other. So I'll go to y equals, and I'll type in for y1 the log of 8x plus 4. y2 would be the right side 1 plus the log of x plus 1. And again, we can just use a log key for these ones because they are common logs. No base indicated, which means base 10. When you hit the log key in the calculator, that's what you're using. So zoom 6 to set our windows to their standard settings. And it's kind of hard to see, but these two graphs will not cross. If we change our windows a little bit, so I'm going to go from negative 2 on the x-axis to positive 10, hit graph. That's a little bit better. It's still not 100% clear that these two graphs don't cross. So let's alter our y min and max a little bit. So for our y min, let's go from negative 3 to positive 3 as a maximum, and hit graph again. So now it's a little more clear to see that these two graphs do not appear to cross. We could make our x max a little bit bigger, say to 25, and a scale of something like 3 on the x-axis. And once again, you can see that that second graph, the colored one, the reddish one, is above the bluish one. Okay? If you try and find a point of intersection, second function trace, number 5 for intersect, enter, enter, enter. There is none. Okay? So sometimes that happens where there is no solution. Question C. So again, I would combine the logs together on the left by adding log base 2 of x minus 4 to both sides. And that just leaves us with the number 3 on the right. So use the product law to combine those. Which when we multiply those binomials out, we'll get x squared, take away 10x plus 24. And now we'll convert from logarithmic to exponential. So again, we'll convert from logarithmic to exponential, which is 2 to the power 3 equals x squared minus 10x plus 24. 2 to the power 3 is 8, so when you subtract the 8 from both sides, you'll get plus 16. And this can be solved by factoring. It'll be x take away 8, x take away 2 equals 0. So x will equal 2 and 8. However, when we look at our restrictions, so for that first term with the log, the argument is x minus 6. So x minus 6 has to be greater than 0. So x has to be greater than 6. On the other side, we have an x minus 4 as an argument. So x minus 4 has to be greater than 0. Therefore, x has to be greater than 4. So we're going to use the one that satisfies both, which is that x is greater than 6. That's the restriction. So that means that 2 doesn't work. That's an extraneous one. Only 8 would work. Let's check this on our graphing calculator. So the left side is log base 2 of x minus 6. So we can put this into our calculator using the log function. You can use that in y1. So log base 2 of x minus 6. And then for the right side, whoops, I forgot the 3 minus this. So let's go to the front. 3 minus log base 2 of x minus 4. So zoom 6 to set our windows to their standard settings. You can see that those two graphs cross. Whoops, and you can find it. Now, notice that I went second function, zoom, then trace. It's asking for the first curve, and it's putting x at 0, and there is no y value indicated because this graph doesn't start till way over here somewhere. Okay, so we're going to have to manually put in an x value, or we can use our arrow key, but I think we can put an x value. Let's put an x value of 8 there. No, it didn't work. Let's try again. Second function, trace, number 5 for intersect, enter. So now I'm going to have to just go over with my arrow key until I see my cursor showing up on that first graph. There it is. Enter, second curve, enter, guess, enter, and there we get our answer at 8, 1. Excuse me, that just confirms that x equals 8 is an answer. Okay? Question D. In this case, we've already got the left side expressed as a log, the right side just as a number. So we can go straight to the step where we convert from logarithmic to exponential. Start with the base and cycle through. So 2 to the 4th, which is 16, equals x plus 3 all squared. And normally when we're solving an equation, and you take the square root of both sides, because that's our next step, we get rid of the square on the x plus 3 by doing the opposite, which is square rooting. Normally when you're solving an equation, you take the square root of both sides, there's going to be a positive and negative root of 16. Positive and negative 4 equals x plus 3. And then when you subtract the 3 from both sides, it can become a negative 3 over on the left. So it'll be negative 3 plus and minus 4 equaling x, which gives us negative 7 and positive 1 as our two answers. But we have a restriction here, and that is that the x plus 3 has to be greater than 0. So x has to be greater than negative 3, which eliminates the negative 7. However, in this case, because the x plus 3 is squared, negative 7 would still potentially work. Because when you let x equal negative 7, plus 3 is negative 4, but when you square it, you get positive 16, which actually will work. So in this case, because the x plus 3 is squared, really what we need to say is that x plus 3 cannot equal 0. And so therefore, x cannot equal negative 3 is the true restriction. So let's check this on the graphing calculator, right? And we've seen that you can use the log function to have a different base if you have that operating system in your calculator. If not, though, then you'd have to use the change of base identity. So if you want to do log base 2 of x plus 3 all squared using the change of base identity, what you might want to do first is bring the 2 in front. Actually, no, we'll just leave it as is. It'll be the log of x plus 3 squared, x plus 3, close the bracket and square it, divided by, whoops, I gotta fix this, because I'm just going to have one equation here. So let me clear this out. One equation on, well, actually that's not true, but I'm going to have to write the log equation as one equation using the change of base identity. So to do that, I'm going to open up a bracket. And on top, I'm going to have log of x plus 3 all squared, log of x plus 3, close the bracket to square it, and then close the bracket that I opened to start with, divided by log of 2. I'm using the change of base identity. So I'm going to open up a bracket here just to make sure I keep this all together. Log of 2, close the bracket on the log on the 2, close the bracket on the log of 2. So this is using the change of base identity. If you don't have the newer operating system and you want to check it on your graphing calculator, you have to use the change of base identity. And that should equal positive 4. So that's my second equation. So now when I graph this, this is what it looks like. I think I did something wrong here because I don't even get one of the answers and they both should work. Log of x plus 3 all squared over log of 2. Log of x plus 3 squared divided by the log of 2. That should have worked. Let me try it again. Log of x plus 3. I'm using the change of base identity. So it's log of x plus 3 all squared divided by the log of 2. using the change of base identity. Same graph. Okay, let me try something else here. I said before maybe we should bring that 2 to the front. So just on the side here, if you have log base 2 of x plus 3 all squared, using the power law, it'll be 2 log base 2 of x plus 3. And then using the change of base identity, what if we did it this way? 2 log of x plus 3 over log of 2. Let's see if that changes anything using the change of base identity. So my first equation will be 2 times the log of x plus 3 divided by the log of 2. And that should equal 4. Okay, so that gives us a graph where at least it looks like 1 is a point of intersection. But we still don't get the -7. However, if you let x equal -7 in the equation, -7 plus 3 is -4, squared is 16, and 2 to the 4th does equal 16. So both equations do work. Not both equations, both answers do work. So I guess what we're learning from this is that sometimes graphing won't always give you whether or not roots are extraneous. Okay, question E. Again, I would start by combining the logs together. In this case, by adding log base 49 of x minus 2 to both sides. And then we can use the product law to combine them because you're adding logs with the same base. Right? You cannot use these laws unless the bases are the same. And so we're going to have log base 49 of x squared plus 2x minus 8. And so now we will convert from logarithmic to exponential. It'll be 49 to the 1/2 equals x squared plus 2x minus 8. And 49 to the power 1/2, well, power 1/2 means square root. The square root of 49 is 7. And when you subtract that from both sides, you're going to get that last term to become minus 15. Because before we solve a quadratic by factoring, we need to make it equal to 0. So the factors here will be x plus 5, x minus 3. And our solutions then would be x equaling -5 and positive 3. If we look at our restrictions, though, for this first term, the log of x plus 4, x has to be greater than -4. For the second term, the log of x minus 2, x has to be greater than positive 2. And we have to choose the one that satisfies both conditions, which is x is greater than 2. And because of that, -5 won't work. Only positive 3 works. Okay. And if we were to check that, using the original equation, and I know we always haven't used the original equation, we've checked these, but it is a good idea, especially as they get a little more complicated or complex. So when we let x equal 3, on the left side we'll have log base 49 of 3 plus 4, which is 7. And this is asking us 49 to what power equals 7, which is a half. 49 to the 1/2, which means the square root of 49 does equal 7. But you can also use your calculator to figure out what that is. Either you use the log function, log base 49 of 7, or you can use the change of base identity, the log of 7 over the log of 49. Either way, you'll get 0.5. On the right side, it's 1/2 minus log base 49 of, when x is 3, 3 minus 2 is 1. So log base 49 of 1 is asking 49 to what power is 1? The answer is 49 to the 0 equals 1. And 1/2 take away 0 does equal a half. Right, so that answer checks. Okay, what about questions like this? So when we talked about solving exponential equations before, and I said, well, the way we did exponential equations before and we solved them, we made the bases the same. And I said at that time, we're going to see how we can use logarithms to solve exponential equations when the bases cannot be made the same. You cannot express 605 with a base of 4, but we can use logarithms to now find out what x is. We did it before by graphing. Okay, what we did is we graphed it. We went y equals 4 to the x as our first equation, and y equals 605 as our second equation. To graph this, our y window must be at least 605 as a maximum, so let's let it equal 620. And maybe we'll change our scale to 50 on the y-axis. So now when you graph it, you can see the point of intersection, you can find it, and it's at approximately 4.62. So that's graphically 4.62. But we can also do it algebraically now by using logarithms, by converting from exponential to logarithmic. Start with the base and cycle through. The exponential function has a base of 4, so when you write it as a log, it'll be log base 4. After the 4 comes the 605. After that comes the x. When you start with the base and cycle through. And when you do log base 4 of 605, whether you use the log function or change a base identity, log of 605, close the bracket, divided by log of 4, you get that same answer, 4.62. So you can use logarithms to solve now exponential equations by converting from exponential to logarithmic. Now for b, you'd first want to get the exponential part by itself by starting with division by 8 on both sides. So that gives us a 3 to the 2x by itself on the left. On the right, 568 divided by 8 is 71. And now to solve this, we'll convert from from exponential to logarithmic. We'll start with the base and cycle through. It'll be log base 3 of 71 equals 2x. And now if you divide both sides by 2, you have x by itself. It'll be log base 3 of 71 all divided by 2. So whether you use the change of base identity or the log function if you have it, log base 3 of 71, and then go outside the bracket to then divide by 2, it's 1.94. So again, if you see the words determine, that would tell you that you need to show your work. You could use your graphing calculator to check it if you want. So for y equals, I'll put 8 times 3 to the power 2x. On the right side, it's just 568. So our y maximum must be at least 568. And it is, I got it set at 620 right now. So when I graph, there's my point of intersection. Find it, 1.94. So you can definitely use the graphing calculator to check, to make sure that the solution you got algebraically works. Okay, let's look at question B on the next page. Again, we'll convert from exponential to logarithmic by starting with the base and cycling through. It'll be log base 5 of 1700 equals x minus 3. And we can get x by itself by adding 3 to both sides. And then use our calculator, right? Even though it says algebraically determine, or if you're asked that, you've done the algebra by converting from exponential to logarithmic. That's showing a mathematical step. And then you also added 3 to both sides. So there's no way that if you want to, you could show that you're using the change of base identity for that first term, log of 1700 divided by log of 5, but it's not necessary. Once you get to that point, you can go straight to the log function if you have it in your calculator. And so to the nearest hundredth, it'll be 7.62. Incidentally, this question, or this expression above it, that's the exact value for x. That would be the exact value that I circled. But this one said to round to 2 decimal places, so that's what we've done. Now C is a little different because both sides are exponential functions. So it makes it a little difficult to start with the base and cycle through. So what we'll do instead here is I'm going to take the log of both sides, right? You can do that. We know that when you have an equation, you can do whatever you want to one side as long as you do the same thing to the other side. So I'm going to take the log of both sides. And now I'm going to use the power law. When you have the log of a power, the exponent can come in front as a coefficient. So that's my next step. I'm going to use the power law on both sides. Bring the exponents in front as coefficients. So we still have some work to do here. But I started by taking the log of both sides, then I used the power law to bring the exponents in front as coefficients. And notice I've used brackets there because the log of 6 is multiplied by both terms. So I'm going to do that. I'm I'm going to multiply out the brackets on both sides. Now remember, we're trying to find out what x is. That's the whole point of this. What is x? So what I'm going to do is I'm going to take the terms that involve x, I'm going to put them together on the left side, and I'm going to put the terms that don't involve x together on the right side. So what that means is I'm going to subtract the log 6 from both sides, and I'm also going to subtract x log 8 from both sides. And so this will now give me an expression where I have all the x terms together on the left, and all the terms that don't involve x on the right. So again, remember, we're trying to solve for x. We want to get x by itself. So on the left side, I have two terms, two completely different terms involving x. Knowing that I need to get x by itself, my next step would be to take out a common factor of x on the left. And now you would simply divide both sides by what's inside the bracket. And that would be an expression for what x equals. So we can do that on our calculator to find out what x is as a decimal. These are all common logs, no base indicated, because we took the common log of both sides as one of our initial steps. So I'm going to use brackets to keep the numerator and denominator together. So 3 log 8, close the bracket on the log 8, minus log 6, close the bracket on the log 6 and the bracket on the numerator, divided by, open a bracket for the denominator, 3 log 6, close the bracket on the log 6, minus log 8, close the bracket on the log 8 and on the denominator, enter. So 1.35 is our approximate answer for x. Which we can check. In y equals, we'll put in y1 the left side of the original equation, which was 6 to the power 3x plus 1. And y2 is the right side, 8 to the x plus 3. Zoom 6 to set our windows to their standard settings, because we found an answer of 1.35, which we can't actually see on our windows. So we have to make our y max quite a bit larger. So in Windows, let's make our y max, I don't know, 200, and change the scale to, let's say, 20. Now we'll hit graph and see if we see the point of intersection. Still not quite. Maybe we'll try zoom fit, zoom 0. Didn't even show the second graph. But let's see if it works. Second function trace, number 5 for intersect, enter, enter, enter. There it does, 1.35. It's just, you can see it just at the very bottom of the screen. So maybe to see it better, if I make my y minimum a little smaller, make my y minimum, let's say, 0. Still can't see it. Second function trace, number 5 for intersect, enter, enter, enter. Again, it gives us our answer 1.35 as an approximate. Now, if you're checking answers in the back of the book, they may simplify this expression that we got here. So let me show you how we would do that. The first thing is I've got coefficients here on both the top and the bottom. I bring those up as exponents. So 3 log 8 is the same as log of 8 cubed minus log 6. Same thing on the bottom. 3 log 6 would be the log of 6 cubed minus the log of 8. So again, checking answers in the back, they may do this step, right, where they simplify the expression. 8 cubed, what is that, 216? 8 to the power 3, 512, not even close. So that's log of 512 minus log of 6 all over log of 6 cubed. There's the 216 minus log 8. But this can be simplified further because on top you're subtracting logs with the same base, so you can use the quotient law. That'll be the log of 512 divided by 6 over, on the bottom, same thing. You're subtracting logs with the same base. You can use the quotient law to combine them. That'll be the log of 216 divided by 8. And I'm thinking both of those fractions can be reduced. 512 divided by 6. Is that decimal math? Enter, enter, converts it to a fraction. That's 256 over 3. Divided by the log of 216 over 8, which is exactly 27. So there's our simplified expression as an exact value. And just to check to make sure we get the same answer, we'll have the log of 256 over 3, close the bracket, divided by the log of 27, gives us the 1.35. Okay, so they may simplify it in order to, again, just write it in a simpler form. It has the same value as what we started with, but obviously it's simpler because you combined as many terms as you could. Okay? So we're going to finish off on Monday on doing some more examples with exponential growth decay, talking about different equations involve logs. We'll do a few questions dealing with interest, compound interest, that sort of thing to finish off this chapter. So that'll be Monday. Tuesday is going to be the quiz on this stuff, chapter 8. And then next Thursday will be the exam on chapter 7, 8. Okay? And remember, tomorrow is the rewrite for trigonometry. So if you're not rewriting, then you'll just have the class to work on some of the other assignments, spend some time studying, getting ready for that next chapter test or unit exam, I should say. So what you can be working on is page 412 to 413, questions 1 through 5, and 8. And I will put those solutions on Google Classroom so that you can check your answers. Okay? Yeah. Did you want to go down to the office, Brighton, and get whatever your mom left for you? Is it food?
No, actually,
Oh.
it's she's. It might be some snacks.
Well, you are a growing boy.
That's what I'm saying.
Yeah.